Hello and welcome to Math with Mrs. Becker. Today we are looking at Calculus Chapter 1, Section 4. We will start looking at something called a limit. Now the definition of a limit. Let our function g of x be a function and a be a number. We say that the number L is the limit of g of x as x approaches a. The big thing you have to realize here is that as you are looking at limits, you need to realize that you are approaching whatever that value is from both the left side and the right side. Okay, it is provided that g of x can be calculated close to the limit for all x that are really close to, but they don't have to be equal to a. In this case, here is the notation. So you are finding the limit of a function as x gets closer to a. I know this is probably a little bit confusing even just looking at the directions, but don't worry, we will go over this and you'll be fine, I promise, okay? Determine that the limit of 3x minus 5 as x approaches 2. We want to find that. So one way just that really helped me back when I was in calculus is making a table. If I make a table, you have to remember that you're approaching from the left and the right, okay? So let's visualize a coordinate plane. We are looking at the x value, 2. So if I am approaching from the left side, as I get closer and closer to 2, we want to see what it approaches. So if I'm making a table, we're going to go ahead and just make sure that we understand this. If I am coming in from the left, I could say like, all right, let's go 1.9. That's pretty close to 2. But 1.99 is even closer. And 1.999 is even closer than that. And hey, let's go crazy, 1.9999. So if we go ahead and we fill these values, we are coming in from the left side, getting really, really close to 2, but not actually touching 2. So what we're doing, and I'll just go ahead and write out the first couple just to make sure you see it, okay? So if I go ahead and I fill this in, 3 times 1.9 minus 5. Okay, so I get 0.7. Now if I go ahead and I go closer to the 2, so 3 times 1.99. So I can go in here and I can insert another 9. Ooh, check that out, 0.97. Okay, so just realizing what we're doing, I'm going to go ahead now and try 0.999. 0.997. Now if I go even closer, 1.9999 minus 5. Check that out, 0.9997. So as you should be able to tell, as we got closer to 2, we went 1.9, 1.99, 1.9999, as we just kept getting closer, but not actually the 2. Do you see where our numbers, they kept approaching 1. Okay, it was 0.7, but then as it got closer to the 2, it got closer to the value of 1. Then 0.997, 0.9997. Every time we got closer to 2, it got closer to 1. That's the idea of a limit. But I can't say that it's 1 yet because you have to make sure that it does the same thing as you come from the left and the right. So let's go ahead. And now if I'm coming from the right side, I just want to do a few of these again just to make sure that you understand what a limit actually means. So if I'm here, I want to approach 2. So if I say 0 or 2.1, okay, that's a little bit to the 2, but I can get closer. I can go 2.01. That's closer to 2. 2.001. That's closer to 2. And if I want to go crazy again, 2.0001. So again, what we're doing is we're filling this value into the function. So 3 times 2.1 minus 5. Let's go ahead and do this. 3 times 2.1 minus 5. I have 1.3. Okay, now I want to get closer to the 2 because we are approaching 2 coming in from the right. So I'm going to go ahead and put a 0 right there. So I have 3 times 2.01. This is 1.03. So notice already it's getting closer, but we want to make sure that it's actually going to get closer to 1. So I'm going to go ahead and insert another 0. Hey, 1.003. It's getting closer to 1. If I plug in another 0, what we're doing is getting closer to the 2. 2.0001 is closer than 2.001. So every time I add a 0, I'm getting closer and closer to the 2. 0.003. So as you can see, this is coming in from the left. As we got closer and closer to the value of 2, our y values we approached was a 1. As I'm coming in from the right, as we got closer and closer and closer to the 2, this also was approaching a 1. So if you are approaching the same value coming from both directions, the left and the right, you could say that the limit of 3x minus 5 as x approaches 2 equals 1. That's what a limit is. Okay, now here are just some rules. There are times where the limit does not exist. And if you saw Mean Girls, you saw that in that math competition. The way that they won is she knew the limit did not exist, okay? So there are scenarios where that is the case. Let's go ahead and look. For each of the functions below, number 1, determine if it exists. If you see a circle, what that means is it's a break in the graph, okay? It is a hole. There is no value. It's not defined at that location. So if I'm looking at A, we want to know, is there a limit as we approach 2? So coming in from the right side, okay, it's approaching 1. Coming in from the left side, as I get closer to 2, it's approaching 1. So here, the limit does exist. We see as x gets closer to 2 from both sides. From here and from here, it's approaching the value 1. So we would say that the limit of that function as x approaches 2, it is 1. It's okay that it's not defined there. A limit means as you are approaching that value from both sides, what is the y value getting close to? If it's getting close to the same value, and in this case it's a 1, it's okay that it's not defined at that location, because from both directions it's approaching 1, and that's what a limit means. Okay, B, if I approach from the right, as I get to 2, it's getting close to 2. As I approach from the left, as I get to 2, it's approaching 1. So the limit does not exist. As you go from the right, it's approaching 2. As we come from the left, it's approaching 1. For a limit to exist, the function must approach the same value. You are approaching 2 different values as you're coming in from the different directions. Okay, so the limit does not exist. Next one, as I come in from the right, oh, it's going to positive infinity. As I'm approaching to the left, oh, it's going to positive infinity. Here, the limit does not exist. Infinity is not an actual value. Okay, so we're looking at an asymptote here. A limit cannot be infinity. A limit cannot be infinity. And that's what those are doing. That's an asymptote. As x approaches 2, the g of x values get larger and larger. They're not approaching a fixed number. It's not an actual value. For a limit to exist, you have to be approaching an actual numerical value, like 1 or 2 or 3. Okay, now here's where this gets a little wild, okay? We will go ahead and look at some examples. Good thing you're watching this video, because if you just looked in the textbook and saw this, it might be enough to throw you over the edge and have you get really, really nervous and stressed out, okay? Don't let this get stressed out. These are just properties, things that you can do with a limit, okay? I'm going to go ahead and provide examples, and you'll notice even with the examples, I'll tell you which theorem we're using, so that way we can have this make sense, okay? So don't see this and panic. Big breath, let's do this. If k is a constant, if you are trying to find a limit and you have a constant, remember a constant is a number, so it can be something like 5 times x squared or 8 times x cubed. What you're allowed to do is take that constant out front, calculate the limit of the function, and then go ahead and multiply by that constant. You are allowed to do that. If you have a function that has an exponent, you are allowed to find the limit of the function. Once you find the limit, then apply the exponent. You are allowed to do that. If you are adding two functions and they want you to find the limit, you are allowed to find the two limits separately, take the two limits, add them together. If you are trying to find the limit of two functions that are right now being subtracted, you can find the two limits separately and just simply subtract the limits. Same thing if you're multiplying. You can you can go ahead and find the two limits, find the limit of f of x, find the limit of g of x, multiply those two limits together. Okay, if they want you to find the limit and you're dividing, find the limit of the top function over the limit of the bottom function. Okay, so let's go ahead and do this. This says to use theorem 2. Okay, so if I am using theorem 2, this says to go ahead and find the limit and don't worry about the exponent till later. So this says find the limit as x approaches 2 of x, then take that limit and we're going to cube it. Okay, so this means I can go ahead and fill in, change the x to a 2. So if I change the x to a 2, the limit would be 2. Okay, I replaced x with the value we're approaching. That makes it a 2. Then I go ahead and I take the exponent, which is a 3. 2 cubed is 8. Okay, so as you're calculating limits, you take whatever the function is. In this case, it is an x. You replace it with the value you're approaching. That's how I got the 2. Theorem 2 says you don't have to worry about the exponent till the end. So now that I have the 2, I can take it to the power of 3 and get an 8. Okay. Theorem number 1. Theorem number 1 says if you have a constant, bring it out front. Here is the constant. So I can take 5 times the limit as x approaches 2 of x cubed. That's what theorem number 1 means. Now again, as you're calculating limits, I can take the 2 and just fill it in. So I have 5 on the outside. 2 replaces the x to the power of 3. 5 is on the outside. 2 to the power of 3 is 8. So your limit, 5 times 8, is 40. What that means is if I graphed 5x cubed, if I was coming in from the left and the right side of 2, the values will keep getting closer and closer and closer to 40. Okay, here's theorem number 4. Theorem number 4. Find the two limits separately and subtract them. So this means I'm finding the limit as x approaches 2 of 5x cubed minus, so I'm going to find this limit, find the limit as x approaches 2 of 15. Okay, if I go ahead and I replace this with a 2, I'm just showing you that you can do all these different things. 5 times 2 cubed minus, there is nowhere to fill a 2 in. This does not have a variable. So that means that your limit would be 15. Now I calculate it. Order of operations, exponents come before you multiply. 2 cubed is 8. 8 times 5 is 40. 40 minus 15 is 25. So if you went ahead and you put this into Desmos and you checked it out, if you graph this, as you are approaching 2 from the left and the right, your values would keep getting closer and closer to 25. Okay? Use theorem 2. Theorem 2 says that if you have an exponent, you can go ahead and find the limit first and deal with the exponent later. That's what I'm going to do. That means that this is really the limit of x as it approaches 2 of 5x cubed minus 15. Remember, a square root is equivalent to an exponent of 1/2. So I can think of that as an exponent instead. Now, if I calculate the limit, you replace the x with a 2. So it's 5 times 2 cubed minus 15. Order of operations, 2 cubed is 8. 8 times 5 is 40. 40 minus 15 is 25. Now you take it to the power of 1/2. Power of 1/2 is the same thing as a square root, and the square root of 25 is 5. So that means if I put this into my calculator or into Desmos, or if I made a table like we did right away today, as we got closer and closer to 2, coming from both the left and the right, our y values would be approaching 5. Okay, let's look at another one. This says to use theorem 6. Well, here's theorem 6. Theorem 6 says that what we have to do is find the limit of the top and the limit of the bottom separately. So if I find the limit as x approaches 2 of the square root of 5x cubed minus 15 over the limit as x approaches 2 of x to the power of 5. Okay, again, yes, I've used the same examples. You're probably noticing that, but I want you to see that there's so many different ways you could do this, okay? So right now, let's just go ahead and fill that in. So it's the square root of 5 times 2 cubed minus 15. Order of operations, you always simplify underneath a radical before you actually take the square root. 2 cubed is 8. 8 times 5 is 40. 40 minus 15 is 25. The square root of 25 is 5. So the limit of this is 5. Now the limit on the bottom, you replace the x with a 2. 2 to the power of 5. 2 times 2 times 2 times 2 times 2 is 32. So there's your limit. If fractions freak you out, take 5 divided by 32 and you would have 0.156. So as you graph this, as you're going closer and closer to 2 from the left and the right, your y values would be getting really, really, really close to 0.156. That's the value that it's approaching, okay? Now these theorems right here, what they're really doing is just showing you what we just practiced. When you have a value that you are approaching, what you're allowed to do is just fill it in for x. So it's saying that whatever this value is, you get to fill it right into the polynomial when you're trying to find the limit. And that's what we just practiced on the other side. Even if it's a rational function. Rational function means that it's a fraction. If you are trying to find the limit as x approaches a, fill a in for x. So wherever you have an x, change it to a. You are allowed to fill it in, okay? So let's just go ahead and take this idea one more time. If I am going ahead and I'm trying to find this limit, one thing you're allowed to do is go into the function itself and change the x's to a 3. So this is 3 times 3 squared minus 1. That is what the limit is. Order of operations. 3 squared is 9. 9 times 3 is 27. 27 minus 1 is 26. So your limit is 26. So if you graph 3x squared minus 1, and you're looking at that graph or making a table, as you get closer and closer to 3 from both directions, your y values are approaching 26. Okay, now here, this is something really cool. Now, if you look at this, typically you'd say, oh, I cannot put a 3 in there, and you're right. But when you're doing limits, you are allowed to simplify first. That's because you're saying as x approaches 3. It doesn't have to get to 3. As you're getting really, really close to 3, like 3.0000001, you can put that in here. You can put 2.9999999, and that's the idea of a limit. You're not necessarily actually getting to this value. You're getting as close as you possibly can. For that reason, you are allowed to simplify first. So if I look here, x squared minus 9, I can factor that. I can make this x plus 3x minus 3. The bottom is x minus 3. So I can go ahead and cross off the group x minus 3 on the top and the bottom. What that leaves me with is as the limit approaches 3 of x plus 3. Now I can fill that 3 in. 3 plus 3 is 6. Because a limit is approaching the value and it's not necessarily equal, you are allowed to simplify rational expressions first. That's what we did here. I factored the top, the bottom could not be factored, crossed up what they had in common. What I had left is x plus 3. Then you can find the limit of that because you can put the 3 in, okay? I know limits are a new idea. Go ahead and try some. The assignment, I just went ahead and said, let's do all of them because it is a new idea. Some of them go fairly quick. If it asks you to do a table, go ahead and make a table like we did right away. Have your x values approach the number that you're looking for, but you have to remember that it is only a limit if you approach the same number coming from the left and the right. So you would have to technically do two tables, one coming in from the left, one coming in from the right, making sure that you are approaching the same value. I hope you enjoyed learning about a new concept today, and I look forward to working with you tomorrow.